Hello mathematicians, we're going to have a look at curve sketching now. And curve sketching is a little bit of an art, and it's through practice that it shifts from being something which is a lot of drudgery to something where we've got little clues. Perhaps we don't even know where the clues come from. But to have some sort of a system is what it's all about. So in our system for curve sketching, there are some things that we tend to look at and roughly in this order, but again, not specifically, and that's where the art comes into it. So these questions that we need to look at include, is it a basic curve? So can we look at it and see that this is just a parabola, hyperbola, etc.? Or is it a combination of basic curves? And that might be something which gives us a clue as to its overall behaviour. If it is a basic curve, has it been translated? Has it been shifted up, down, left, right? Has it been reflected in the axis with a negative sign and so on? The things which were back in the earlier part of the prelim course. Are there any restrictions on the domain? So I often go to this one first of all. So if we've got a quotient or a square root, look at how that restricts the domain. Are there x and y intercepts we can find? Now, nearly always we can find the y-intercept. Sometimes we can find the x-intercepts, although when you get much past quadratics, that can be really difficult. Are there any stationary points? So we take our first differential and see whether there's a spot where the first differential equals 0. And what is the nature of the stationary points? So we can find the second differential if it's relatively easy to find, and notice its sign to work out whether we've got a maximum, minimum, or possible point of inflection. Or if the second differential looks hard to get, we can just use a table of values of the first differential either side of the stationary point. We can determine and investigate further any possible stationary points of inflection. So they're the points where our first and second differential equals 0, and we need to check what's happening in terms of concavity and slope either side of those points to be sure of what they are. And we can also determine straight points of inflection. So that's where the second differential equals 0, but not the first differential. So these will be points where concavity changes on our curve. Asymptotes we've already mentioned. Limits, particularly where we go towards plus or minus infinity, or where we've got vertical asymptotes as determined by restrictions on the domain. And if there's an element of symmetry, so if we can see that we've got an odd or an even function, that may just save us a little bit of work. And finally, if all else fails, or even if it doesn't, plot a few easy points so that we can be sure where the graph is at particular points. But always remember, look for questions that are similar to ones that you've done before. They may be a guide to you. So you can see that I've adapted how I'm going to write these solutions now, because you don't need to watch me write, and that the solutions are going to become longer and longer and longer. So if we want to plot y equals 9x minus x cubed, then almost as a reflex, these are the things that we do. So we see if we can find where we cut the axes. So we cut the x-axis when y equals 0, and y will equal 0, where if we factorise the original equation, we can see y will equal 0 at x equals 0 and x equals plus or minus 3. So we know these points straight up. Then we find the first differential. So we know we find that so that we can discover if there's a place where the first differential equals 0. So from this we factorise it, rely on our difference of squares. We can see then that we'll have stationary points when x equals plus or minus 3. So what's the nature of these stationary points that occur here and here? Well, if we can find the second differential easily enough, which we can here, then we see what the second differential does at these stationary points. So where x equals plus root 3, that second differential is a negative, which means that we've got a curve which is concave down, so it's a maximum turning point. At x equals minus root 3, our second differential is positive, so it's concave up, so it's a minimum turning point. So we go ahead then and find the y-coordinate associated with our turning points, plot those points, and we can see that our maximum and minimum, when we've got all of our clues together, we just put in the curve. Now for our next curve, which we've encountered before, you might remember, we again look at our original function. We can see that at 0 and 4 we've got vertical asymptotes, so we don't cross those vertical lines. We cut the x-axis where y equals 0, and if we try to find a value of x which gives us y equals 0, there isn't one because the top is always 1. So there are no roots. We're not going to be cutting the x-axis anywhere. So if you like, we're only ever going to be able to approach that axis asymptotically, perhaps. So we've put in our asymptotes here and here, roughly. Now, first differential, so we've got the quotient rule, put it on the bottom, square it, up the top, multiply by the differential at the top, minus, put down the bottom, put down the top, multiply by the differential at the bottom, tidy that up, and we want for a stationary point y dash to equal 0, which means we want the top of our y dash to equal 0, which happens when x equals 2, which, if we work out the y value, is at -1/4. So when we mark that point in there, and knowing that we never cut the axis, we know that we have to be confined within this little box, if you like. But this is a maximum value. Well, actually, we don't know that it's a maximum value yet because we haven't got the second differential. And this thing looks pretty horrible. I don't want to get the second differential of that. I could go and do a table of values, as I think we did in our earlier example, but instead I'm just going to take the fact that we never cut the axis and look at limits to try and get this curve. So if I first of all, so I can deal with the piece in the middle here, look at the limit as x tends to 4 from the negative side. Then if I look back at my original function and put a number a little bit less than 4 in there, you can see that I'm going to be dividing by a very small negative number. So that will give me 1 divided by a small negative number. It will be -infinity. And likewise, if I approach 0 from the positive side, I will get, by plugging that into there, -infinity. So I get this part of my curve in that case. And then as I tend towards 4 from the positive side, when I put that in there, that will give me a very small positive number on the bottom. So I'll tend to +infinity. So that's this part. Why won't that pen work? So it's this part. And as I tend to +infinity, then we remember how to take the limit as we go to +infinity. I divide through every term top and bottom by the highest power of x. And then when I put x equals infinity into this, I'm going to get 0. So my curve shoots off asymptotically towards the x-axis. Likewise, if I look at what happens when I tend towards -infinity for this thing up here, I'm going to head off towards 0, as I can see down here. And as I tend towards 0 from the negative side, I'm going to find that I shoot off to +infinity. So my curve is going to shoot up here. Now for my last example, this is starting to get fairly complicated. So I cut the x-axis where y equals 0, so that will be at x equals 0. And I can see that I'm going to have an asymptote at x equals +1. So I've got my asymptote in here. I'm definitely going to pass through 0, 0. So I then go and get my first differential with the quotient rule. And when I simplify that first differential, I'll get this. Now what I can see is, in terms of critical points, that at x equals -1, the first differential doesn't exist, which fits with common sense. No curve, no differential. But at x equals 0 and x equals +2, we're going to have stationary points. So So if I work out the y values associated with those, it's 0, 0 and 2, 4. So I can mark those 2 points that I know my curve goes through. And now I can investigate those stationary points. So I could go ahead and take my second differential. So I've done that here. It's pretty horrible. Having done it, I could then just put 0 and 2 into it to find out what happens in terms of the sign. But I can also do it with the table of values. So whichever way we decide to do it, I'm going to discover that at 0, 0, if I put values either side of that and find y dashed, I'm going to discover that I've got a maximum turning point, and at 2, I've got a minimum turning point. What happens as I shoot off towards infinity? Well, as I tend towards infinity, for this curve here, as always, divide top and bottom by the highest power, and I notice that as I tend towards infinity, my equation actually becomes y equals x. So what I have here is an oblique asymptote, that as I go to infinity, certainly the x values tend towards infinity, but more than that, the y values tend towards x. So if I try to put all of those clues together, then I'm going to get the curve looking like this just here, where I'm trapped, if you like, within this little section here, but down here I pass through this stationary point, and if I'm going to head off to y equals x, but it's a maximum, I've got to be on this side of the line. So it's quite a difficult example. I think, again, on the edge of what would be reasonable for extension 1. So have a go at these. As always, this book will throw all the curly ones at you that it can, and these ones here, 9 to 12, really only worth looking at if you've got aspirations of doing extension 2. They're way too hard for extension 1.